Uh, so, dear, once again, good morning to one and all present over here. Today, we want to study about the relationship between the acid dissociation constant Ka and base dissociation constant Kb. So, today we shall study about the relationship that is developed between the acid dissociation constant Ka and base dissociation constant Kb. We are aware Ka and Kb represent the strength of an acid and a base respectively. The more is the value of Ka, the stronger is the acid. The less is the value of Ka, the weaker is the acid. The more is the value of Kb, the stronger is the base. The less is the value of Kb, weaker is the base. In case of the conjugate acid base pair, you know what is conjugate acid base pair? Suppose you have an acid Ha, and if it loses its H plus and produces H plus and A minus, then this Ha, which is an acid, this Ha is an acid, and this A minus is called base, and Ha and A minus are called conjugate acid base pair. So, my dear students, here we understand the meaning of the conjugate acid base pair. The acid which, when it loses its H plus, forms something, that something which is formed is the conjugate base for that acid, and this pair of this acid and its conjugate base is known as the conjugate acid base pair. They are related in a simple manner. This acid and its conjugate base pair, they are related in a simple manner, so that if one is known, the other can be deducted. So if you know the acid, you can easily find out what is the conjugate base, or if you know the conjugate base, you can easily find out what is an acid, and their concentration can also be calculated, or they can be easily found. Now let us understand it in detail, considering the example of NH4 plus and NH3. My dear students, when this NH4 plus loses its H plus, when it loses its H plus, it forms a base NH3, which is ammonia. So this is what it is, the acid base pair, my dear students. This is what it is, your acid. This is what it is, your base. And this is what actually is known as the conjugate base. So the pair of NH4 plus and NH3 is the conjugate acid base pair, my dear students. You know that NH4 plus, when it reacts with water, it produces H3O plus and NH3 minus. For this equilibrium, we can write the acid dissociation constant Ka, that is the concentration of H3 plus multiplied by the concentration of NH3 divided by the concentration of NH4 plus. So on calculation, my dear students, we found that the value of Ka for this particular acid, that is your NH4 plus, is found to be 5.6. Can you read this? Dear student, can you read it for me? Can any of you read this for me? Nobody is interested. Okay, the value for this is found to be 5.6 into 10 to the power minus 10. So the value for the Ka for NH4 plus is found to be 5.6 into 10 to the power minus 10. This is how we understand. Now, my dear students, we want to find out some relationship between Ka and Kb. Let us move forward. Now, for this particular, suppose ammonia, when it reacts with water, it produces NH4 plus and OH minus. Here ammonia behaves as a base, it accepts H plus from the water, and thus it behaves as a base. So, and this is the conjugate acid. For this equilibrium, my dear student, we can easily write the Kb, and for Kb you can write the concentration of NH4 plus multiplied by the concentration of OH minus and divided by the concentration of NH3. Now on calculation, the value of Kb in this case, my dear student, is found to be 1.8 into 10 to the power minus 8. This is the value we find for this Kb here. So if we add both the reactant, so if we add NH4 plus and NH3 minus, or if we add both these reactions, my dear students, we are going to add both these reactions. This is reaction number 1, this is reaction number 2. So when we add both these reactions, what happens here? You can see that this NH4 plus, which is underlined with the green color, and this green color, both have same, so we can remove both of them. The one which is underlined with the red color, that is ammonia, that we can remove. One H2O plus one H2O, it gives us 2 H2O. We have this H3O plus and this OH minus left with us. So actually, when this both reaction, when we add, it is actually the self-ionization of water, which we can even represent it as this, in this manner, my dear students, that H2O plus H2O, that gives us H3O plus and OH minus. This H2O donates H plus, and this H2O turns out to be H3O plus, and this is what it turns out to be, OH minus. For this ionic product we write, that is the concentration of H3O plus and OH minus, and we have this value, that is 1.0 into 10 to the power 14, where K represents the strength of NH4 plus, and that is an acid, and Kb represents the strength of ammonia, that is, which is a base. Now it can be seen from the net reaction that if we multiply the value of K and Kb, so for K we will write H3 plus multiplied by NH3 divided by the concentration of NH4 plus. For Kb we write the concentration of NH4 plus multiplied by the concentration of OH minus divided by NH3. Now you can see that by doing this simplification, just by doing a simplification, we can find out that Ka multiplied by Kb is equal to the concentration of H3O plus multiplied by the concentration of OH minus is equal to Kw is equal to 1 into 10 to the power minus 14. So we can write it, my dear students, the value of K and Kb, even we write the value of K and Kb, that is 5.6 into 10 to the power minus 10 multiplied by 1.8 into 10 to the power minus 5. We even get the same answer for this, and that is 1.0 into 10 to the power minus 14. So my dear students, now we can write that the product of Ka and Kb is nothing but Kw, which is equal to the concentration of H3O plus multiplied by the concentration of OH minus, and for that we can write the numerical 1.0 into 10 to the power minus 14. So this is how, my dear students, it's quite clear to us that we have this relationship between the K and Kb. I should write it Kb, I'm sorry. K and Kb, that K multiplied by Kb is equal to Kw, and the value is 10 to the power minus 14. It is also related to the concentration of H3O plus and OH minus. Instead of H3O plus, we can even write concentration of H plus and OH minus, and that is also, it is known as the Kw. So this is how, my dear student, we understand exactly the idea of the relationship between Ka and Kb. Let's move forward and understand it in detail. So my dear students, now we can say that Ka multiplied by Kb is equal to Kw. Now if we take logarithm both the sides, so minus log of K multiplied by Kb is equal to minus log of Kw. Therefore, minus log of Ka plus minus log of Kb is equal to minus log of Kw. For minus, as we know that minus log of H plus, we write PH. So minus log of Ka we will write Pk, minus log of Kb we will write Pkb, and minus log of Kw we will write Pkw, and finally we get Pka plus Pkb is equal to Pkw. Now we know that Pkw is equal to minus log of Kw, that is minus log of 10 to the power minus 14, which gives us the value of 14, and thus we can say that at 298 Kelvin temperature, my dear students, the value of pK plus pKb is equal to pKw is equal to 14. So if you can recall, my dear students, we had this formula derived that pH plus pOH is equal to 14. Now we can even say that pKa plus pKb, that is also equal to 14, and both these are pKw. So even pKw will also have the value is equal to 14. Please remember these equations, and they are very useful for the various calculations. This can be extended to make the generalization. Now whatever we have understood, we can write it a general form for them. Let us see what is the generalization for this, whatever we have seen. The equilibrium constant, my dear students, the equilibrium constant for a net reaction obtained after adding two or more reaction equal to the product of the equilibrium constants for the individual reactions. So if you add more than one or two or more than two reactions which are at equilibrium, then the when then their equilibrium constant or and then you get the net reactions. Once again I am trying to tell you, when you add more than two equilibrium reactions with each other and you find out the net reactions, the equilibrium constant for net reaction is the multiplication of the equilibrium constant of the various equilibrium reactions that you have added to each other. Once again, when you add the two equilibrium reactions with each other, the net, and you find out the net reactions, the equilibrium constant for the net reaction is actually the product of the equilibrium constant for reaction 1 and reaction 2. But suppose you add more than two reactions, then what happens? So let us see. Suppose one reaction takes place in n step. So suppose you add n various reactions at equilibrium. So at each step, the equilibrium constant is K1, K2, K3 up to Kn. So now you are adding the various n equilibriums to each other, and you have various equilibrium constant K1, K2, K3, K4 up to Kn. Then you find out the net reactions, and the equilibrium constant for net reaction, we write it as a K net, and therefore my dear students, K net is equal to K1 multiplied by K2 multiplied by K3 multiplied by up to Kn. This is how we can generalize this equation for addition of the various equilibrium reactions with each other. And this is how, my dear student, we truly understand the process here. Now my dear students, we want to prove Kw is equal to Ka multiplied by Kb. Now before we move, my dear students, I would like you to ask me if you have any doubt. Dear students, whatever I have explained, do you understand it or not? And if you find any doubt, you can ask me now. Or should we move forward? बच्चों, अगर आपको कुछ समझ में नहीं आया तो प्लीज पूछ लीजिए. हेलो, एटलीस्ट आंसर तो दीजिए. क्या आप मुझे सुन पा रहे हैं? कैन यू हियर मी?
Yes, sir.
Do you understood it? Like, do you understand it or not?
Yes, sir.
Is there anyone who could not understand it? कुछ पूछना है तो पूछिए. एटलीस्ट बता दीजिए सब समझ में आ गया है.
Yes, sir, understood.
Please, dear student.
Yes, sir.
Okay, let's move forward then. You understood everything, right? Now let us solve. Thank you. Let us solve one problem, my dear student. That prove that, suppose you are asked in the exam that prove that Kw is equal to K multiplied by Kb for base B. So for base B, my dear students, we can write that B, when added to water, it produces the conjugate acid BH plus and it produces OH minus. Please remember that this B and BH plus are the conjugate acid base pair. For this equilibrium, my dear students, we can write the equilibrium constant Kb is equal to BH plus multiplied by the concentration of OH minus divided by the concentration of B. Please remember, when we write the equilibrium, when we write the base dissociation constant, we do not write the concentration of H2O, because the equilibrium constant K into H2O, that is what we have written as a Kb. So this is what I would like to bring it to your notice, my dear students. Now let's move forward and understand the next. Multiplying both the numerators and denominator with H plus. So here we want to multiply both this numerator and denominator with the H plus ion concentration. So let us, just for understanding purpose, let us do it that way, that we multiply both the numerators as well as denominator with the H plus. So multiplying both the numerator as well as the denominator with H plus, my dear students, we get Kb is equal to BH plus, concentration of BH plus, multiplied by the concentration of OH minus divided by the concentration of B multiplied by the concentration of H plus. So here we have multiplied both of them with the concentration of H plus and H plus. We are well aware that, my dear students, we can write it in this form. This term we will write it together. So we will have OH minus and H plus. Then what is left with us, that we will write it separately, BH plus divided by concentration of BH plus divided by the concentration of B multiplied by the concentration of H plus. So when we write this concentration of BH plus and concentration of B multiplied by the concentration of H plus, we would realize, my dear students, that we have base B and its conjugate acid BH plus. So we have this base, our base is B and conjugate acid is BH plus. So for this conjugate acid BH plus, we can write an equilibrium such that BH plus gives us B and H plus. For this, my dear students, we can easily write the equilibrium constant or acid dissociation constant, that is Ka is equal to B, concentration of B multiplied by the concentration of H plus divided by the concentration of BH plus. Thus, my dear students, if we take an inverse of K, my dear students, suppose we write it 1 upon K, then we would write it as a B, concentration of BH plus divided by the concentration of B multiplied by the concentration of H plus. This is what it happens. So for this value we can write 1 upon K. Now let us push this value of 1 upon K into this equation. You can see that in this equation we have this value BH plus divided by B, concentration of B divided multiplied by the concentration of H plus. These two are exactly same. Please look into that. You will realize that these two are exactly same. You can see these two, you can correlate them. These two values are same. So we should put 1 upon Ka instead of that. So here we will write 1 upon Ka, and finally we will get Kb is equal to the concentration of OH minus multiplied by the concentration of H plus into 1 upon Ka. So this is what it is going to be our next equation. So what we can write here is this, that this Kb is equal to, dear students, this Kb I am talking about, this Kb is equal to concentration of OH minus multiplied by concentration of H plus, and this value, for this value we can write 1 upon K. So we will get, and concentration of H plus and concentration of OH minus, we collectively write Kw for this. So we can write Kb is equal to Kw multiplied by Ka, and we can even write Kb is equal to Kw divided by Ka, or we can write Ka multiplied by Kb is equal to Kw. So this is how, my dear student, we understand the various, we understand how we can prove that Ka multiplied by Kb. Now we want to study something else, which is, we have the next question. Before we move to the next question, my dear students, I would like to ask you whether you have understood it well or not. If you have any doubt, you can ask. So let us solve this problem. Let me read the question for you. Determine the degree of ionization and pH of 0.05 molar of ammonia solution, the ionization constant of ammonia can be taken as Kb is equal to 1.77 into 10 to the power minus 5. Calculate the ionization constant of conjugate acid of ammonia. So here you need to find out see what things you are given. Determine the degree of ionization and pH. So first of all, you need to find out the degree of ionization. Then you need to find out the pH. Then you are given the concentration C, that is 0.05 mole of ammonia solution. The ionization constant of ammonia can be, ammonia is a base, so we are given the value of Kb. Calculate the ionization constant for conjugate acid. So, and you need to even find out the value of Ka. So my dear students, these are the things that you need to find out, and these values are given to you. So let us use these various values to identify or to find out the answers. Let's move forward. You can see that we are given the concentration of ammonia, that is 0.05 mole per liter. We are given the Kb value for it, and conjugate acid of NH3 plus is NH4 plus. So you can see that NH3 plus when reacts with H plus, it gives us NH4 plus, and for this reaction we need to find out the equilibrium constant, that is acid dissociation constant. We need to even find out alpha, we need to find out the pH, we need to find out the Ka for this. So for that, let us look into the solution. For base NH3, we can write NH3 when it reacts with water, it produces NH4 plus and OH minus. Now my dear students, the concentration of NH3 is given initially, that is 0.05 molar, which is C. The initial concentration for product is 0. Now we know that the change that we write, my dear students, the change that we write is generally minus C alpha for this and plus C alpha for the products. But you know the value of C is 0.005, so we would write 0.05 alpha or 0.05 alpha, 0.05 alpha for both of them. So by adding this, we can find 0.05 minus 0.05 alpha is the equilibrium constant for the reactant, whereas for both the products, the concentration is 0.05 alpha. Now alpha is known as the degree of dissociation, and C, that is 0.05, is the concentration of ammonia initially. For that base, we can write Kb is equal to concentration of products divided by the concentration of reactant. Now when we put the values for the concentration, for NH4 plus, we write 0.05 alpha. For OH minus, we write 0.05 alpha. And for NH3, we write the concentration 0.05 minus 0.05 alpha. By taking 0.05 common into the denominator, we get Kb is equal to this equation. Now we can easily say that 0.05 divided by 0.05 is equal to 1. And the final equation what we may get is 0.05 alpha square divided by 1 minus alpha. Now my dear students, we know that alpha is nothing but your degree of dissociation, and degree of dissociation for a weak base is very small in number. So we may take this, that 1 minus alpha is approximately is equal to 1 because the value of alpha is very small. So looking into the very small value of alpha, we will find out 1 is quite greater than the alpha, and therefore Kb is equal to 0.05 alpha square divided by 1. This, it was 1 minus alpha, which we have taken as a 1. And therefore, my dear students, our Kb is equal to 0.05 alpha square. Therefore, alpha square is equal to Kb divided by 0.05. And therefore, alpha is equal to square root of, we can put plus or minus, square root of Kb divided by 0.05, and that is the value of Kb is 1.77 into 10 to the power minus 5 divided by 0.05. For 0.05, my dear students, we can write 5 into, okay, now you can see both the numerator and denominator have the same number after the decimal place, and thus by removing the decimal place, we have written them, and then we have done the various calculations so that we can find out our alpha is equal to 1.88 into 10 to the power minus 2. Now we know that the concentration of OH minus is 0.05 multiplied by alpha. So doing this multiplication, we can find out the concentration for our OH minus. Same way, we are well aware that the concentration of H plus and OH minus is 10 to the power minus 14, and therefore the concentration of H plus is equal to 10 to the power minus 14 divided by OH minus. Ultimately, that leads to the value of H plus, that is 1.6 into 10 to the power minus 11. And we know that pH is equal to minus log of H plus. By putting the value of concentration of H plus, that is 1.06 into 10 to the power minus 11, we can find out pH is equal to 10.97. So this is how, my dear student, we understand the value of pH. We are well aware that Ka multiplied by Kb is equal to Kw, and therefore Ka is equal to Kw divided by Kb. For Kw, we have the value 10 to the power minus 14. For Kb, now we can write 1.77 into 10 to the power minus 5, which gives us the value of Ka, that is equal to 5.64 multiplied by 10 to the power minus 10. So this is how, my dear students, we truly understand the theory with one example. Now, my dear students, we may have di and polybasic acids or di and polyacidic bases. To understand that, let us understand their definition. Some of the acids like oxalic acid, which is H2C2O4, or you can even represent them oxalic acid in this manner. Then you have sulfuric acid, which is H2SO4. Then you have phosphoric acid, which is H3PO4. You can see that these acids have more than one H to be dissociated or to be ionized. So they have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic acids. So those acids which have more than one H plus or more than one proton available, they are known as the polybasic acid. For example, if we have dibasic acid H2X, then the ionization process for dibasic acid H2X, we can write H2X first gives H plus and HX minus. This HX minus again dissociate to give H plus and X minus. So it is a two-step reaction, and we have two different reaction 1 and reaction 2 we find out. For the reaction 1, we can write Ka1 is equal to the concentration of H plus multiplied by the concentration of HX minus divided by H2X. For equation 2, my dear students, we can write Ka2 is equal to concentration of H plus multiplied by the concentration of X minus 2 divided by the concentration of X minus. This is what you can observe it from this equation, my dear students, that for this equation we have written Ka1, and for this equation we have written Ka2. Please remember, my dear student, here that our various values that we have seen for Ka1 and Ka2, we call Ka1 as the first ionization constant, and we call Ka2 as the second ionization constant. So here in the first and second ionization constant, my dear student, we can understand the value for Ka1 and Ka2. Now depending upon this, my dear student, we can understand the example of H3PO4. You can see that, my dear students, that H3PO4 first dissociate in H plus and H2PO4. You have the value of K1 7.5 into 10 to the power minus 3. Second, H2PO4 minus dissociate in H plus and HPO4 minus. We have the value of Ka2 6.2 into 10 to the power minus 8. We have HPO4 minus 2, which gives us H plus and PO4 minus 3. The value of Ka3 is equal to 4.2 into 10 to the power minus 3. So now, my dear students, if you compare these three values of K1, K2 and K3, you will realize that the value of K1 is more than the value of K2, and the value of K2 is more than the value of K3. You can understand it very easily. So that is what we want to discuss next, that it can be seen that higher order ionization constant is smaller than the lower order ionization constant. So we can say that K2 is less than K1, K3 is less than K2, or we can say that the value of K1 is greater than K2 is greater than K3, or the value of K2 is greater than K3. Now what is the reason for this? The reason for this is that it is more difficult to remove a positively charged proton from a negatively charged ion due to the electrostatic forces. So when we get the ions formed, it is difficult to remove the positively charged ion from the negative ions, and that is why it takes more effort, and that is why the dissociation decreases. Polyprotic acid H2X solution contain the mixture of these various ions. This acid contain the mixture of these various ions, that is H3O plus, H2A, Ha minus and A minus 2. If H2A is a strong acid, H3O plus in the solution mostly come from the H2A. So, my dear students, if you look into the various concentrations or various ions, mostly these H plus ions or H3O plus ions comes from the first dissociation, or comes from the first step of dissociation of the acid. That is what they wanted to tell you. In the second dissociation, the production of H plus or H3O plus ion is very small as compared to the first dissociation, and that is why the value of first ionization constant is very high as compared to the second or third one. Now, my dear students, we want to study about the very important point, which is known as the factors affecting acid strength. So, my dear students, we want to study about the factors affecting acid strength. Let us study what are the various factors that affect our acid strength. Having discussed quantitatively the strength of the acids and bases, we come to a stage where we can calculate the pH of a given acid solution. But curiosity arises, or we may be curious if we are very interested in study. Do you find yourselves curious, my dear students? But curiosity rises as why should some acid be stronger than others? So why some acids are stronger and why some acids are weaker? What factors making the stronger acid and stronger base? So what is the factor that really affects the strength of any acid or strength of base? So on the basis of that, my dear students, let us try to see what are those factors that really affect, what are those factors that affect the strength of a particular acid or a particular base. Let us find out the answer. Let us find the answer. If we find answer in a few lines, we would come to know that extent of dissociation of an acid depends on the strength and polarity of the acid Ha bond, or this bond polarity or this bond strength is the major reason for the acid strength, my dear students. In general, when the strength of Ha bond decreases, that is, the energy required to break the bond decreases, it becomes stronger acid. So the less stronger is the bond between H and A, the acid is going to be stronger. If the bond between H and A is strong, then it requires more energy, and that is why the acid is a weak acid. Ha becomes the stronger acid when the strength decreases for this bond. For this bond, if the strength decreases, the acid becomes stronger. If the strength increases, the acid becomes weaker. Polarity increases for bond, Ha bond, that is the electronegativity. Now we need to understand about the polarity. So when the polarity increases, so polarity increases for Ha when Ha bond or bond Ha, when what happens when the polarity increases, that is the electronegativity difference between H and A if increases. So if suppose you have Ha bond, and when the electronegativity difference between H and A increases, the polarity increases. So if the electronegativity difference between H and A increases, my dear students, there is a marked charge separation. Thus the cleavage of the bond Ha become easier, and then the acidity increases. So if the electronegativity difference between H and A is more, acidity is more. But it should be noted that acid strength in a group, while now we want to study the acidic strength while going down the group. While comparing the elements in the same group, please remember, while comparing the element in the same group we are talking about, the same group of the periodic table, Ha bond strength is more important factor. So when we study the acidic strength in a group, my dear students, HA bond strength is more important factor as compared to the polarity, my dear students. As the size of A increases down the group, HA bond strength decreases and acidic strength increases. So as we go down